Okay, these are the Math 3, Unit 5, Section 4 notes. Today we're talking about normal distribution, the empirical rule, also known as the 68, 95, 99.7 rule, and z-scores. These all go hand in hand, so it seems like a lot, but we'll use all of them together. So, besides the fact that the curve is continuous, one property of the normal distribution is the area under the curve. So the area under this curve represents the probability of several events happening. So the total area under this curve is equal to 1, which means 100%. So the likelihood of this happening is or a likelihood of a certain value means the area under all of this is going to add up to one whole, which means 100%. So we can represent these as decimals or as percents. We're going to represent them as percents today. That's why we have the rule 68, 95, 99.7. So the empirical rule helps us to normally distribute our data. And it states that almost all the data will fall within 3 standard deviations of the mean. So if my mean is directly here, then all of my data will be within 3 standard deviations away. So when I calculate a standard deviation, then I can move that amount away in each direction, and almost all of my data should fit inside there. So the rule, the reason why it's 68, 95, 99.7 is that 68% of the data will be within 1 standard deviation from the mean. So if I start at the middle, 1 standard deviation to the right and 1 standard deviation to the left represents 68% of all of the data that I have. So this darkest shaded region is 68% of all of my data, and it is 1 standard deviation from the mean. Then 95% of the data will be within 2 standard deviations from the mean. So 2 standard deviations in either direction all together is going to represent 95% of our total amount of data. And then 3 standard deviations away is going to represent 99.7% of our data. So almost 100%, not quite, with a little bit left over, but almost, that's why it says almost all the data will fall within 3 standard deviations. So as you can see, this is a normal curve. It's what we call a bell curve. It's curving the same way on either side. 50% of my data is on the left, and 50% of my data is on the right, half and half. And that's all the way to the end. That means a few numbers might, like one value might be on the outside. Depending on how many pieces of data we have, there might be some data that lies outside here. Okay, so let's see what the area is of each of these shaded regions, because if 68% of my data is within 1 standard deviation away, that means half and half. If I split 68 in half, 68 divided by 2 is going to give me 34% being 1 standard deviation to the left of the mean, and 34% being 1 standard deviation to the right of the mean. So make sure you're following along, otherwise it's kind of hard to read what numbers these are. So you want to really be listening to what numbers I'm putting in here. So 34 and 34 adds up to 68, or in other words, 68 divided by 2 gives me this part here. Now, between 1 standard deviation and 2 standard deviations away, I'm not going to divide this 95 by 2 because I only want to find the area that's in this middle shaded region. But I know that from here to here, from 2 standard deviations away in either direction, that's 95%. And from 1 standard deviation away is 68%. So I'm going to subtract those. And when I subtract those, I get 27. So that means that this middle, like gray shaded region, and this one on the left as well, those both add up to 27% because all I did was take my 95% and subtract my middle of 68%. But there's 2 different sections, so I'm going to divide that by 2. And I'm going to get 13.5% on either side. So that's a 13.5%. 13.5%. Some videos that you might look at online might round that up to 14. Please leave it as 13.5 so we can get our most accurate data. You'll see videos that do a catchy song or saying that go 34, 14, 2, and they'll do something that rhymes, like, but just please make sure that you know that 13.5 is the actual number that we have here. Okay, and then if I'm getting these outside pieces, I'm going to take 99.7 and I'm going to subtract everything that we've already calculated, which is our 95%. So 99.7 minus 95% leaves me with 4.7. So these 2 last regions add up, or not last, but add up to 4.7. So if I divide that by 2 for either side, because I have 1 on each side, then that's going to divide to 2.35. So I have 2.35% here. And 2.35% on the other side. Okay, but if I add all these up, 34 plus 13 plus 2.35, that doesn't amount to 50. I have a little bit on the outside left. So when we say almost all of the data fits within 3 standard deviations, it's not quite everything, so we need to figure out what percent is on the outside of 3 standard deviations away. So if I then take the entire amount of data, which would be 100%, and subtract my 99.7, then I would get 0.3. And what would happen if I split that on either side? Yeah, I would divide by 2 and get 0.15. So this is 0.15% and 0.15% on the outside of 3 standard deviations away. So that's only 0.15%, not even of a whole. So if we were talking about in decimal form, that would be 0.0015 of my data is on the outside. So that's why we say almost all of it is under this curve that is within 3 standard deviations. Okay, before we start practicing that, we also want to talk about z-scores. So a z-score is a number of standard deviations a value is away from the mean. So before, I was able to determine whether a piece of data was within 1 standard deviation away, or 2 standard deviations away, or 3, but now I can determine the exact place away it is. by using the z-score. So a z-score will be positive if it's to the right or negative if it's to the left, because we're talking about a direct. Going to the right is positive and to the left is negative. It's not a distance. We need to account for the direction. So if we're going to the left, it has to be negative, and going to the right, it has to be positive. All right, so all of these symbols you already know. We've done this in other sections. X is your score compared to the mean, so that's your piece of data. So that's your score. Let's go ahead and just highlight that. This mu symbol is the Greek letter mu. It's like a cursive M. That stands for the mean, and you know that. And then this lowercase sigma, Greek symbol, stands for standard deviation. So we're going to use this formula to calculate z-score, and that'll tell us how far this specific piece of data is from our mean in terms of standard deviations. So how many standard deviations is it away? Go ahead and flip to the other side. Example 1, a research was performed on the IQ scores of a private firm with 800 employees. So that's our N. Remember, N stands for the number of data that we have. In this case, it is people. Our data is different people. The scores are noted to be normal in distribution. That means our bell curve will help us to determine some answers to different questions that we have. The mean of the distribution is 100. I'm just going to write down our mean equals 100. Make sure you're using your symbols to get used to that. And the standard deviation is 15. Okay. So we're just going to split all this up. So all these lines that are here, you can go ahead and draw them straight up, because we are going to do the area under the curve for each of these. And we want to fill in our values. So you need to remember how to set up this bell curve. Remember the 68, 95, 99.7 rule in order to distribute this data. So we know that 68% is in the middle, so this is 34% and 34%. Then 95, 34 plus 34 is going to get subtracted from our 95, and we're left with 13.5 on each side. Then next, we have 2.35 on either side, because 99.7 gets subtracted by 95 and then split in half. And then 100% gets subtracted by 99.7, and we're left with 0.15% on each side. Remember those numbers. Okay. The mean of the distribution is 100. These represent how far in standard deviations you are from the center, which is always the mean. So you put your mean in the middle. If I go to the right, that is 1 standard deviation away. If I go to the left, that's 1 standard deviation to the left. So I want to add a standard deviation to 100. My standard deviation is 15, so 115 is to the right. If I subtract to go to the left, then 85 would be 15 to the left of 100. 2 standard deviations away means you add 15 twice. So then we get to the next value of 130. You can just add the 15 to the previous standard deviation away. So Adding 15 twice to 100 gives me to 130. Adding 15 3 times to 100 gets me to 145. That means 145 is 3 standard deviations from our mean of 100. To the left, we're going to subtract 15 each time we go to the left. So 85 minus 15 is 70. 70 minus 15 is 55. 70 is 2 standard deviations to the left of our mean of 100. You can also write that this is the mean there. 55 is 3 standard deviations to the left of our mean. So you can, these are standard deviations away. Standard deviations from the mean. So now we can start answering questions based off of this bell curve because it represents our data and where our data lies. What approximate percentage of scores are between 70 and 130? Percentage of scores, these are all percentages, so we just have to add them up. Between 70 and 130, we add up all of these values. So 13.5 plus 34 plus 34 plus 13.5. But we also know that this represents 2 standard deviations away from the mean. So our 68, 95, 99.5 or 99.7 rule states that this is 2 away. Let's go ahead and write 68, 95, 99.7. 1 away, 2 away, 3 away from the mean. So 2 away from the mean would be 95%, but you could just add up all these percentages to get that number. What approximate percentage of scores are between 85 and 115? Between 85 and 115, those are 1 standard deviation away from the mean, so that's 68%. You can add up the 34 and 34, or also know that the 1 standard deviation away means 68%. What approximation of scores are between 85 and 130? This combines different values. That's why it's good to break this all up. So 34 and 34 is 68. 68 plus 13.5 is 81.5. What approximate percentage of scores is less than a score of 100? So less than 100 is everything to the left of the mean, and we know that if it's normally distributed, half of our data is to the left of the mean, and half of our data is to the right of the mean. That's what normal distribution is. Later in the year, when we talk about test scores and how you score on a specific test for the state, they normally distribute the data so that half of the people in the state are on one side and half of the people of the state are on the other side. So they're comparing you to other students and how other students in the state perform. So you want to just do better than everyone else. All right, approximately how many employees score between 85 and 100? How many employees? So this is not saying what percentages. On A, B, oh, sorry, we skipped D. Let's go back to D. What approximate percentage of scores is greater than a score of 115? So anything to the right of 115, 13.5, 2.35, 0.15, all of those added together, 2.35 plus 0.15 gives you 2.5, plus 13.5 is 16. so 16%. All right, so A through E asks about your percentages. If you're answering as a percent, you just have to add up the percent that you have listed there, because these are all percentages. But if you're asking about how many employees there are, we need to find out how many people are actually within that value. So we know between 85 and 100, that's 34% of my employees. 34% of the employees, and there are 800 employees. So how do I find 34% of 800 people? That's right, we do 800 times 34%. Now if I multiply by a percent, I should multiply by the decimal value. Good, so we move the decimal 2 places to the left, otherwise it gets way too big. 800 times 0.34 gives me 272 employees. Okay, how many employees scored between 55 and 145? So back up to the top, between 55, which is over here, and 145, which is here, that is our 99.7%, because it includes everything within 3 standard deviations away. So 99.7 of our people, 800 times 99.7%, means if it were multiplying, we need to change our percent to a decimal, which would be 0.997. And that would give us 798 employees. You're taking your percentage and you're multiplying it by your total number of people in order to find out how many people this question applies to. You could find out the 0.15% of each and then subtract it from the total, but that leaves room to make an error, because you don't want to multiply by 15%, you want to multiply by 0.15%, which would be 0.0015. So don't forget to move the decimal. But you would also have to add those together, which would be 0.3. All right. Approximately how many employees scored greater than 70%? Or sorry, greater than 70. So the score of 70 is here, so how many people are above 70? Let's find all of these values. We have everything except for all this on the left. So 68. Everything but 2.5, because these two add up to 2.5. So 2.5 subtracted from 100% would be 97.5. If you want to do that on the side, you can do 100 minus 2.5, and you get 97.5. I thought that was easier to find my percent to just subtract the 2 instead of adding all these up, but if you're going to have a calculator on your test, so you just add those together. All right, how do I find 97.5% of 800? I move the decimal to the left to multiply as a decimal. Multiplying those together, I get 780 employees. If an employee scored 110, what is the employee's z-score? Which means I have to list my z-score formula. So x minus mu over sigma. All right, x is the score. So remember, we're doing the score minus the mean over our standard deviation. The score is 110, the mean is 100, and the standard deviation for this problem, if you remember, is 15. So that gives me 10 over 15. And we're just going to go ahead and write it as a decimal. So my z value, 10 divided by 15, gets me 0.6 repeating, so I'll just round that to 0.67. If an employee had a z-score of -1, what is the employee's IQ score? So let's set up the same formula by plugging in a -1. We don't know the score, which is x. We do know we're going to subtract the mean, which is 100, and we're going to divide by the standard deviation of 15. Now we have a formula, or an equation. How do I solve for x? Multiply both sides by 15. When you multiply 15 times -1, you get -15. 15 and 15 reduce, because 15 over 15 is 1. So I'm left with x minus 100. What do I do with my minus 100? Good, add it to the left side. So I get x is equal to 100 plus -15, which is 85. So this employee's IQ score is 85. All right, go ahead and flip to the other side. In a normal distribution of Ford F-150 prices, 99.7% of buyers paid between $25,000 and $37,000. State the mean and standard deviation. I don't know why there's a question mark. It should be period. All right, so let's go ahead and set up our normal bell curve. Our mean is not given, but our data is normally distributed. So we're going to start with our range. So 99.7% of buyers is our 3 standard deviations away. So that's 1, 2, 3, 2, 3. So that's 25,000 on the left and 31,000 on the right. Okay, now we need to figure out our mean, which is right in the middle of those values because the data is normally distributed, which means it's even. So how do I get halfway through this data? Well, I'm going to subtract and then find how to get to the center. So I'm going to subtract those and I get 12,000. So the distance between these values is 12,000. How many increments do I have? 1, 2, 3, 4, 5, 6. So if I have 6 increments, what happens when I divide this number by 6? I'm incrementing by $2,000 each time. So if 12,000 divided by 6 is 2,000. So each time I go up, I'm going to go up by $2,000. So 27,000, 29,000, 31,000, 33,000, 35,000. I'm writing down the wrong numbers. This is 37,000, which is why when I subtract I got 12. Sorry, I was looking at my key. Some of you were probably subtracting that, wondering where 12,000 came from. 37,000 minus 25,000 gives me 12,000, and then my increments are by 6, so I'm going to divide by 6 to see how much I'm incrementing by each time. All right, so my mean is the one that's right in the middle, right? So my mean is 31,000. My standard deviation is my increment. If I go one standard deviation to the right, how much did I increase by? We know that all of our increments were increasing by 2,000 each time, so that's my standard deviation. State the mean and standard deviation. There's our answer. Example 3. Suppose your class recently took an exam in Math 3. The average score of the class was 75%. Sounds about right. The standard deviation for the class was 10.3. Let me write these down as we come across them. So 75 for the mean, 10.3 for the standard deviation. You scored a 93%. How many standard deviations from the mean is your score compared to the rest of the class? How many standard deviations is your mean compared to the rest of the class? If you're ever asked that, that means you're finding the z-score. So your score is 93. Remember, your data is represented by x. So the score is x. So for finding the z-score, we're going to take x minus the mean, or the score minus the mean over the standard deviation. That gives us 93 minus 75 over the standard deviation of 10.3. All right, so subtracting those, I get 18 over 10.3, and I'm going to divide those and leave it as a decimal. So your z-score is 1.75. And what does a z-score mean? Z-score is how many standard deviations you are from the mean. So 1.75 standard deviations from the mean. The average temperature in Clovis for July is 85 degrees. That's an average. So that's my mean. With a standard deviation of 7.5 degrees, meaning how spread apart the data is can be 7.5 degrees spread apart. One day in July was only 73 degrees. That's a data value. How many standard deviations away from the mean is 73 degrees? So my z-score is 73 minus 85 over my standard deviation of 7.5. 73 minus 85 is a negative number. Be sure to make sure you show that your z-score is negative. So you have to leave the negative number in there. So negative 12 divided by 7.5 is negative 1.6. So you say negative 1.6 standard deviations from the mean. Okay, go ahead and flip to the last page. One of the many useful aspects of the z-score is the comparison to different populations. Look at the example below and try to answer the questions involved with the example. Trisha just found out what her score was from her AP Economics final. It was an 89%. The class average on the exam was a 70%, with a standard deviation of 10.3%. In her AP Physics class, she scored a 73%, and the class average was a 68, with a standard deviation of 1.8. What was Trish's Z-score on her AP Economics class? We're going to find out answers to different questions, so we need to list our data for AP Econ and AP Phys, or Physics, so that we don't mix up our data as we go. So in Econ, her score was 89, the average was 70, and the standard deviation was 10.3. In Physics, her score was 73, the average was 68, and the standard deviation was 1.8. If we're just looking at the data, which class has scores that are a lot closer together? AP Physics. So if the standard deviation is 1.8, that means everyone scored really close to the C range. She's pretty close to the C range. She's at D+ right now. If it's more spread out, then, or if it's 10.3, that means it's more spread out. So not as many people are as close to the 70% range. Sorry, she scored a 73, so she's above the average. Okay. Her Z-score, we're going to do her score for Econ, which is 89, minus the class average for Econ, which is 70, over the standard deviation. 89 minus 70 is 19, divided by 10.3 is 1.845. For Physics, her score is 73 minus the average over the standard deviation. So 73 minus 68 is 5 over 1.8. Her standard, or her Z-score, 5 divided by 1.8 is 2.778. So her Z-score is 2.778. And those are both equal to Z. So that just means how many standard deviations she is away from the mean. In terms of Z-scores, which class did she perform better? Which class did she perform better? In terms of Z-scores, because her Z-score is higher in Physics, that means on a normal distribution, she's more than 2 Z-scores to the right. And then on Econ, she was almost 2 Z-scores to the right. So it's her compared to the class. So when you say compared to the class, which is what a Z-score is talking about, then she scored higher than most of her class on both exams, but the Z-score is higher on Physics than it is on Econ. So she outscored more people, or more percentage of her class in Physics than she did on Econ. So in terms of Z-scores, she did better in AP Physics. Because she had a higher Z-score. And you can tell me that she scored better than more percentage of the people in AP Physics than she did in AP Econ. How would you describe her performances on the two exams comparing both scores? It seems as though she did better on Econ because her Econ test is an 89 and her AP Physics test is a 73. But as compared to her class, she did better in physics. So comparing her scores, she did better in AP Econ. Because 89% is higher than 73%. She got a B plus compared to a C. Last question. A sample of jeans has a mean price of $90 and a standard deviation of 15. Find the price of the jeans that corresponds with each of the z-scores. So we're going to set 0 equal to, well, the mean is 90, and the standard deviation is 15, so we need to find x. So x minus 90 over our standard deviation of 15. Multiply the 15 to the other side. (15 times 0 is 0. These reduce. So we still get 0 equals x minus 90, which means x is equal to 90 if you add it to the other side. And we're talking about prices, so if we're finding the price of her jeans, the price if the z-score is 0 is $90. You need to solve the next 3 problems either in your groups or on your own. Please make sure you're setting your z-score equal to the price minus 90, which is the mean, over the standard deviation of 15, and do that for all of them. Your homework's on the board.